teaching model number 2, we will use an analogy to see how isotopic mass and percent abundance can be used to calculate the average atomic mass for an element. The following layout is taken from teaching model number 2. Let us say we're interested to determine the average age of a typical Chem 112 class with 15 students. This table shows the number of students at a particular age to the nearest integer. By the way, in case you didn't know it, the letter A is the non-SI unit for years. One approach would be to add all the representative ages and divide by 6. This gives a number of 21.5 years. Perhaps you can see that this is a faulty approach, as it does not consider how many students are at a particular age. That is, it's not a weighted average. In the next calculation shown, labeled number 1, we determine a weighted average in that we account for the 5 students who are 18 years old and the 2 students who are 19 years old, etc. This gives us a more appropriate weighted average of 21.1 years. Please note, of course, that assuming students all have integer ages, no one student will have this specific age. This is an important idea to be thinking about when we turn our attention to atoms. Of course, this approach works well if you can count all the entities, in this case students, but this approach will not work directly for atoms because there are too many to count. Let us modify our calculation. In the calculation labeled number 2, we've changed all the multiplying numbers, that is the number of students at each age, to fractions, which of course we can do mathematically because these numbers were all originally being divided by 15. On the next slide, I show this calculation number 2 again for reference. I now change the multiplying numbers to be a fraction out of 100. 33.3 divided by 100 is the same as 5 divided by 15. Now each of the multiplying numbers is shown as a fractional percent abundance. This calculation would work then if we had a class of, say, 700 or 1500, where it would be difficult to count all the students. We just need to know what percentage of students are 18 years old or 19 years old. To calculate a weighted average, one needs to simply multiply each age by the fractional abundance and then sum these numbers. This approach can now be applied to atoms. Please consider the key questions 4 to 5. You may wish to pause the video. On the next slide, I show our calculation 3 as a reference. To answer key question 4, I include a portion of the table of isotopic data relevant to boron. To calculate the average mass of a boron atom, which of course is a weighted average, I take the mass of each isotope and multiply by its fractional abundance. So I multiply the 10.0129 atomic mass units by 0.1978, not 19.78%, but 0.1978. I multiply the 11.0093 atomic mass units by 0.8022. I show the intermediate step of these calculations so you can see that the product numbers should have only 4 significant figures. The sum of these numbers therefore gives an answer where I am allowed only 3 digits past the decimal place. The average atomic mass is equal to 10.812 atomic mass units. This is in agreement with the value presented on the periodic table. Note that none of the boron isotopes actually have this mass. So a reminder again, the masses presented on the periodic table are average atomic masses. They're not atomic masses of individual isotopes, nor are they mass numbers. In part 4c, you're asked to derive a more general equation for this calculation. Here is the calculation we just did again. I will label each term with a symbol. M1 for the mass of one isotope, M2 for the mass of a second isotope. I will use the symbol Fa for fractional abundance, but any letter would do, such as X, Y, or Z. Therefore, Fa1 is used for the first fractional abundance, Fa2 for the second fractional abundance. Here is the general equation. If there are more than two isotopes, simply extend to Fa3M3, Fa4M4, etc. This equation is not found on your formula sheet. Therefore, you may wish to add it for later reference. To complete this video, let us attempt exercise number 1. On the slide, I present the question, the appropriate equation involving 3 isotopes, and the required data from Teaching Model 1. You may wish to pause the video to attempt the problem on your own. We now fill all the required values. Note that each of the percent abundances are changed to a fractional abundance. The isotopic masses are multiplied by the fractional abundances. Significant figure rules tells me that I'm allowed 2 digits past the decimal place in adding these numbers. The final answer is 24.3 atomic mass units, which is in good agreement with the value on the periodic table.